All right, let's get started here with this video. Welcome back to the series. Welcome back to the stream. Really appreciate you checking us out and sticking with us this long. I know it's been a long, boring process, a lot of boring paperwork, but unfortunately it's necessary. If you like what we're doing, definitely like and subscribe. Hit that bell icon on YouTube to get notified of any videos we upload. Let's be crazy and overambitious. Let's shoot for 1 million subscribers by the end of next year, by the end of 2026. You know what? Let's just be crazy. Let's just throw the algorithm for a loop and just hit 1 million subscribers. Let's just do it. Just because it'd be kind of cool to really mess with the algorithm. So in the last video, we pretty much completed what I would say the initial test plan. We're probably gonna end up kind of renaming these in the long run, because we're gonna devise another test plan and another test log for the more deeper, the more destructive testing that we're going to do, because it's going to involve a lot more things. But one of the things I wanted to cover and touch base on and update and fix is I failed to put in some things for traceability. So we're going to kind of insert some rows. We'll clean all these up. Let's just get these up there. Let's clean them up, and we'll go through and explain what we're doing. So one of the requirements that goes along with traceability, so again, while we're having board serial numbers and we're doing all this, is also we should have traceability when it comes to the tools and the equipment that we use to do any testing and or production testing that goes out the door. So one of the general rules of thumb is if it's a piece of equipment like a measurement testing equipment, such as a multimeter, power supply, if it's going to be used in a product that is going to go to the customer or to validate or verify, one of the important things is calibration and traceability. Now, unfortunately, at the same time, I'm not ISO certified. I'm not working towards that at this very minute, but it's nice to have all this kind of written in. So in ISO clause 7.1.5, it talks about the monitoring and measuring resources, and they need to be verified and calibrated prior to use against, what you expect to put out the door. So in other words, in simple speak, it means pay another company money to come in and use fancy equipment to say, yes, that your power supply, when you set it to 12 volts, it puts out 12 volts. When you set it to put out 2 amps, it puts out 2 amps. Basically, that's all you're doing, is you're paying a company to come in, use highly sophisticated equipment and techniques to test your equipment and put a sticker on that says, hey, it was calibrated, it's been verified, but it's traceable through NIST, which, if I'm not mistaken, is National Institute for Science and Technology. So you'll hear of Standards and Technology. So National Institute of Standards and Technology. So basically, if you see a piece of equipment like online, you go buy like a meter or something, and you'll see that it comes with a NIST certificate of calibration, like from the factory. That's what that's referring to. So they're like the de facto standard when it comes to how devices are supposed to operate, within parameters and stuff. You just NIST.gov. So just for just so you can see. So this is basically what they set the standards that you're calibrating your equipment to. Then these calibration companies come in, they'll test your equipment, and they'll compare to the standard, make sure you're within the standard's tolerances. Then they'll issue a certificate along with, other forms of proof that your equipment was calibrated. Unfortunately, it's the name of the game if you're going to be going into ISO certification and manufacturing. It's a requirement of ISO, and if you want to become certified, you have to do it. So Unfortunately, it's a money game. And to play with the, when you want to move into the bigger field, when you want to move from the small pond to the big ocean and play around in there and swim around with those sharks, you've got to play by their rules. You want to step out of your small backyard pond and reach these bigger markets. This is the game you're unfortunately going to have to play. Companies are going to expect it. Customers are going to expect it. So it's just something to prepare you for down this road. If you want to grow a company, an empire, to do this type of work, get ready. This is the stuff you'll have to deal with. But for now, starting out, maybe your first 5-10 years, maybe, depending on your plan that you wrote, that you're envisioning for yourself, you don't have to worry about it. But it's nice to be prepared and already kind of roll in some of the practices. So we're going to update the log to also indicate the equipment we're using. So let's go ahead, merge these guys. We're going to center. And I'm going to go and give it that nice light blue. So what we're going to do is test equipment log. Let's get rid of those, get rid of those. All right, so we'll clean up, we'll add more lines in here as we need to. Zeros above, doesn't really matter. So I like about, again, Excel is I can push Control Y and it'll repeat the last action. So let's see here. No, let's see. I want to see if I can insert. Nope. Because we're going to need enough room. Now, what I could do is just go down here and select all this and drag it all down. But let's see here. All right, we're going to merge these guys. So this is going to become, let's see, equipment or device. Let's just call it device. Geez, I can spell. Device. And cells. Make a model. So center. Might actually have enough for everything that we need. I just yes. Go ahead and do that. Make model. Whoa, what the hell? What in the world are you doing to me? Arial 10 point. Arial 20 point. What in the world? I probably just hit make model. Serial number. What in the world did I just do? Jeez Louise. Arial. What in the world did you just do? Okay, so anyway, make model serial number. Date. ID. So calibrations are typically only good for, I think, a year. So even if you do buy a piece of test equipment that comes with a NIST certificate, it's only good for X amount of time. The certificate should tell you how long it's good for. But like I said, I think it's typically only a year. So calibration, even though we're not going to have, even though we're not going to have calibrated equipment, we're not going to worry about that. We still will track the device, the make, model, serial number, so the device, the multimeter. Make would be like Agilent, the model, serial number if you can find it, calibration date, calibration ID. So usually when you get a piece of equipment calibrated, they will stick an identification sticker on it to let you know, to keep track. Next calibration date. Usually it'll also have all the details of when it was done, when it expires, etc., etc. These are just going to be kind of like empty for now because there's nothing else we should need for this. Maybe I'll just make that into a... So let's just make it into a big block that does nothing. Story of my life. Big block that does nothing. All right. So we have the calibration date. So let's say that'll be, and this is only for test and measurement equipment. So like power supply, multimeter, any other meter, things like that, light meters or whatever you might be using. So there's not going to be too much you have to fill in here. So even though the test plan calls for a lot of different things, the other things that you really need to worry about logging are like your power supply, your multimeter, temperature gauge, things like that. Now, oddly enough, typically anything that gets used for actual manufacturing also gets calibrated. So, and I'm not kidding you, soldering irons do. Because it has happened where customers have requested to know what temperature you're actually soldering at. And they want your records to prove that your irons do. It's a thing, especially when you start getting into medical, military, and aerospace. You start getting weird requests, things that you don't think anybody would be asking about. And yes, things like ESD mats, like the little ESD work mats, the green and the blue ones that you find everywhere, those get calibrated. So one of the things we set up at one of the last companies I worked for was an ESD floor. So they're basically multiple ways you can do it. One's like a ESD static dissipative epoxy that goes on the floor, and that's a process to put down. And then there's another product which are individual like tiling mats, I guess you could say. They're made with an ESD material, and they interlock together, and then they all tie together to at least one or two ground points. And they dissipate. So basically think of it as like a very large static bag that you're walking on. An ESD bag, the silver bags. So, and that actually got calibrated. Believe it or not, that actually got calibrated to make sure it meets the minimum resistance requirements to dissipate static electricity from an operator. That we did that because it made it easier for an operator, for the technicians on the SMT line, to wear an ankle strap, well, a shoe strap, ankle strap, whatever. So basically, you attach it's basically like a wrist strap you put around your ankle, and then there's a part you put on your shoe that makes contact with the mat, like a special shoe strap, and you effectively are connected to the ESD mat through your foot, through your shoe. And it makes it easier so you don't have to an operator don't have to constantly connect and reconnect a wrist strap to a ground point on a piece of equipment. So it just makes operating a little smoother and easier for the technicians that have to do it. It's an expensive option, but I think it's one that's well worthwhile in an actual manufacturing environment. Because ESD control is a big deal because it falls under protection of devices. So basically integrity. Let me look, ISO clause on. I'm just going to look it up. So while there is no, let's see, I'm trying to find out what clause. I was trying to find out what clause calls out for it, but I think it's in there somewhere. I can't remember, but an organization needs to develop a comprehensive ESD control program for personnel grounding, equipment grounding, things like that. I'd have to. It is a requirement that a lot of customers will have anyway, regardless. So just prepare for that. So you'll have to have mats, wrist straps, grounding points that are proper and validated and tested and calibrated down the road. There are stations designed to test ESD wrist straps and things like that. So it's just stuff to be mindful of. It's good to get into practices like this now, like with ESD control and all that, because a lot of components can easily be taken out by discharge. So here we go. Let's go here. Ensure that the logged in the it is recorded. Let's not double. Yep. So one thing you can do to make life a little easier for yourself is with this, and there's nothing wrong with it. So if you've got like a benchtop power supply, so there are two ways you can do this and deal with this, like for testing logs and stuff. One is if you've got like benchtop power supplies, you can always make a label with the serial number and all the relevant information somewhere easy to see. So you don't have to keep flipping over trying to find the model number, the serial number, and all that. It's all easy there. It's all right there in front of you on a label. There's nothing wrong with that. It's not against ISO or anything. Or one of the other things we did is at the last company, one of the last companies I worked for is, so we made specific products for specific customers. And, you know, that was one of the product lines we carried. Most of the stuff we sold wasn't our own internal design. It was, you know, customers requested, we custom engineered and manufactured the products for them. Some of them were aerospace. So for some of these products, we had dedicated test stations for them. So we had dedicated test rigs. We had equipment left just for that test process. So you didn't have to log the equipment down. It was like pretty much hard coded into the test plan or the test document, the test process. So it was logged somewhere that we were using this multimeter with this serial number, you know, with this model number for this test. They were designated specifically for that test. And they weren't moved for anything else. That equipment was bought just or manufactured by us for that test. Because we had to make a couple of our own test jigs and stuff, like a couple of like big project boxes with switches and stuff to do certain controls, like mimic inputs and stuff. So that stuff was done by us. And that's one way is you can have your test process hard-coded all that. And it can be permanently hard-coded in a log file. So that's what we're going to do here. We're going to insert rows above. We're going to kind of insert one more row above. We're going to kind of row below. There we go. That's what I want. So we're going to go through here and kind of clear formatting. Oh, okay. Clear that up. Expand on that might as well. All right. That way we kind of have that break between there and here, like we do everywhere else. That way it kind of looks consistent. Well, there we go. That way we kind of have consistency. It just looks like it flows better. So that's what I wanted to do here. And pretty much any test log will have a similar thing. So that should be it for this guy. So I can stay there for a minute. Let's go here. So test plan. So I guess what we can do then is, there's nothing else I'm trying to think that we should test. So this should validate whether or not the design works and that all the subsystems are playing along nicely. So I don't think there's any other subsystem tests we need to do, any other immediate test with this. We got firmware to write, but that's not really a problem. Again, I got to get all that figured out. I got to get all this stuff figured out. Life just gets in the way, and that's unfortunately the way it goes. So I guess one of the things we can do then is, you know what? Let's get rid of that traceability matrix. We really don't need it. That is a waste of time and resources now that we're kind of doing it differently. Projects. Get rid of that. We do not need that. So then, what I suspect we could start writing then are the more invasive, more possible destructive tests. Basically, after running through this process, it says, hey, your design's good, it works. You're, to go ahead and build up more boards for additional testing. That's basically what it is. What it's telling us. So what we're going to do then is come here. We're going to create a new file. T1201 dash so that one's technically like an initial verification test plan. We can call this one a deep test plan or destructive test plan. We can name it whatever we want. So I'm just going to call it deep plan. Then what I'm going to do is make life a little bit easier. Open this up. We're going to save a copy. Deep test plan. We're going to open it. All right. Oop. All right. So, all right. Let's go ahead and close out the other one. Deep test plan. What we're going to do is we're going to kind of like leave those headings for now because it'll just be easier that way. We will clean that up. All right. So this is going to be the deep test plan. So this is going to, so what I'm going to do is I'm going to come over here. Product initial test plan. So what we're going to do all right. Let's grab this. Product deep. Okay. 1228. Okay. Define design to validate the Extreme to validate the extreme operating conditions and safety of the project assembly. So that's the purpose of this. We're going to design to validate the extreme operating conditions and safety features of the project assembly. So we might clean that off. Clean that up. So the schematic bomb. So yeah, that's a good thing still to have. Full events. So we still need that. We still want that. Infrared temperature gauge would still be handy to have, even though we didn't use that in the last device. So let's go over here. Let's get rid of it. Oh, that one. We don't need it. Don't need that. We'll need that. Okay, let's go here. Here's just appropriate USB. We might need that. USB. I'll leave this stuff here for now, just in case we need to pull it in. All right, a fresh copy of Deep. It is. All right. Okay. So let's go close this guy for now. Oh, save it. Burp. All right, let's open up the PRD real quick. So functional performance. Again, we're not really looking at this stuff, but we're going to kind of rewrite some of this motor current output. I'm not really worried about that right now. Now, did I... Are we looking at ripple? Or did I fail to put ripple in here? You know, we can cover ripple in here. That's fine. Voltage regulation ripple, that's fine. We'll cover that in here. Thermal. Nice. Devices. That's going to be logged into the test plan and need that. So safety, reverse polarity, yep. Thermal protection, yep. We're going to kind of push that. We're going to see what happens when we apply voltage to the outputs. This I'm going to kind of drop right now because it's not for and I hate you. Stop. I hate my mouse sometimes. So I got these, it's a programmable gaming mouse, and some of the buttons I keep forgetting to reprogram. No. Oh, my goodness. Half the fun is me trying to keep it all together. All right, so functional requirements, that's a visual, blah, 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 blah. So, performance requirements. yeah, so I have to get some voltage readings. Like I said, figure out the resistors necessary for this. Thermal log. That's just thermal verification. Okay. So try to figure out the best way to put this. So performance requirements. Okay, requirement identifier. PR 1, 2, 3. PR-1. Requirement. So up to 2.5 amps. Measured. PCB. Oops, 0176 C. Ambient. I don't know why I put that period in there. It doesn't need it. And this guy is voltage. Okay, so we're gonna break this guy down to PR-004. 3.3 volt. And then ripple. Right. Yeah, my plans down the road are to buy a better oscilloscope, like a nice, at least a 2-channel. Who knows? Might buy one sooner than later. See if one's on sale. Who knows? Maybe they're still having kind of like after Christmas deals. Maybe I'll go and get one. We'll see. I'm gonna make some plans, see what I can do. But I mean, I do have my picoscope. All right, so that's that. So 3 and 4. Purple. Less than total. More. Less than. Well, all right. So definitely break those apart because there are 2 separate power supplies on here. So, okay, we don't need the test plans. So let's go and copy that heading. And that is going to be performance requirements. Requirements. All right. Brilliant. So, PR-001. So for performance requirement 001. Move this off to the side because I mean, it just makes it easier for me to read and see what I have to do. Okay, PR001, which is okay with the okay. We're also gonna need the reason is we can also use 2 channels. I think we can decode RS-485. I'll have to check. I know we can at least look at the at like a differential signal and watch it work, but I think you can actually do decoding with some of these nicer scopes. But I have to check. I have to see what I can, what kind of what scope I want to pick up, what I'm willing to pay for. Sorry if you hear me drinking. I apologize. So we're gonna need that with the yeah, so I can spell a bulb. DC and the so we're gonna need some tests to throw on the board. We're gonna have to have some firmware that can test this stuff to constantly drive the stepper motor. I mean, it's gonna fake like it's driving a stepper motor. So what we're gonna do is we're gonna take since we're driving 2 coils, what we're gonna do is we're gonna put do the math. We're gonna see what kind of. We'll have to double check the output voltage, and we'll do the math on the to get the to get it to source the current with resistors, with power resistors. We'll find out what resistors I need to do to get or to set up to get it to basically force that current output, the 2.5 amps. But I'll do all that, and the 20 volt CC and the limit to 3 amps. Because remember, we want to try to actually pull 2.5 amps to the motor driver. So we need to make sure the power supply is set to be able to actually deliver 2.5 plus overhead for the rest of the subsystem. So 3 amps should be enough, but you know what? Let's go to 3.5. Let's make sure we cover enough overhead to operate the ESP32 or anything else. Connect the to the power supply. Let's see here. This will power up. CN1. Just copy and paste. Gosh dang it. Control C. I hit Control C. CN internal. The internal to on the PCB assembly. And I'll put. Actually, no, we're not gonna. All right. Connect the. We're not going to power it up yet. So we're going to connect one. I'm going to have to define all this, but we're just going to. Here's what I'm going to do is I'm just going to kind of do this. Just to remind myself I need to update it. Connect one power resistor unit to the motor. stepper test. CN7, terminal 1 and 2 to CN7 to terminal 1 and CN7 2, then connect one to we're gonna need to be able to measure current. So I'm gonna have to probably build like a little test jig, or like a little. I'm gonna have to wire up like a good thing that we bought extra connectors, pluggables. So I'm gonna have to wire up one so that we can put an ammeter in between. All right, wire. We're going to change this, so we're not that connect the rewired motor driver loading assembly to CN7. So we're gonna have to basically throw a multimeter, use a multimeter in here, because I want to actually be able to try to verify the current draw. And I have to see how we do that. Either by steps. We'll figure it out. That's something I'll have to figure out, do some testing, but we'll have to make a pre-wired motor driver loading assembly to CN7. Out. Jesus criminy. SP32 flash the with the. So we're going to come back in here. Come back up here. Firmware. So we have basic modules. And then deep testing. So deep testing. I'm going to have to clarify all that in these plans. We'll have to create a folder for stepper current. So we're going to have to write some firmware for stepper current. Basically, it's going to try to drive the stepper motor and try to just deliver enable that output so it goes through the loading resistor and actually pulls the current, and we'll with the ammeter kind of test for it. Flash the stepper current firmware. So if things work the way I remember, think they do based off of the data sheet for the stepper driver, there's a good chance that constant current will cause the unit to possibly overheat, and it should trigger a shutdown/fault condition. So we're gonna have to kind of set up the firmware to monitor that fault. I would like to do a fault condition test on this. I want to see what easy conditions we can do, what kind of faults it's able to detect. Because if one of the faults you can detect is an unconnected stepper motor, we can test that easy. But and update the prior test plan to actually test for that, and that's the way we can test the fault detection. Again, this is fluid because we need to know more about what we're working with, what we're testing. So stepper current firmware. All right. Connect the USB to FTDI cable to the is it J4? Look for the FTDI. J4. Yep. Now, I say proper polarity. Jesus Christ, I can't spell. Technically, if you have it backwards, it's just not going to work. It's not going to hurt anything. You're not going to fry anything because the pin assignments, you're not going to damage anything. So if it's backwards, it just won't work. You won't get communication. This is just to help avoid any frustration when tying it together. Connect USB, FBI. Okay. Load up putty and open the COM port with the settings. Baud 8 data bits, no bits, one stop bit, no parity. Reset the PCB. And the terminal should display following message. P 10122022501. Stepper current testing. Okay. So it'll display that. That way, you've got the proper firmware loaded. So at this point, you don't have a multimeter attached. It'd be ideal to have two separate multimeters to watch two separate channels, but we're just going to be basically watching one at a time. Basically, motor output A and then motor output B. We're just kind of looking at them both, but we're really just trying to push it to the limit. See, make sure it can. I'd like to be able to do both at the same time, but with current readings, it's easier to actually do it in series rather than trying to pick it up inductively. In DC, it's harder to pick up inductively than you can with AC. AC, it's easy to pick up inductive current measurement. With DC, it's difficult because the voltage is only traveling one way. If I'm not mistaken, it is possible, but it's just harder to do. Display the following message. Connect. Okay. Place the play into current mode and attach the code's correct input ports. Then connect the red with lead. So it's only going to be able to measure. No, it should be able to measure positive and negative current. That's not a problem. So it doesn't really matter, but we're just going to kind of follow the positive lead to the motor driver loading assembly to the number one and the black, the number 2. Okay, so that connects the current meter into series with the stepper motor driver output, at least on the first output. And we'll say this is going to be A. In the window, type the command start. Enter. This will start the process and load down the meter and meter for current detected. So current measured. So everything goes right. Let me fix this here. Boom, boom, part. So if everything goes right, what will happen is you'll connect all this up. You start the test. It'll start trying to drive motor output 1 or A. And the resistor network, the resistor will load it down, force it to try to source the 2.5 amps. And we want to observe what happens. Now at the same time, do we want to try to do another test? No, we're just testing this. So, does the other test for PR2 temperature rise? That's kind of like more normal operation, not when you're pushing this to the limit. This is technically going to be pushing this to the limit. Again, I have to look at the data sheet to see if, what failures cause a failure, a fault condition. And we might be able to rate that into the firmware. And it can flash the status LED or whatever based on a fault. So if it triggers a fault, we might be able to look for it. And because I don't know what all faults are there, I have to double check. Because this is actually, honestly, the first time I've actually started playing around with, I actually wired up the fault output on that driver chip. I've only used it in like one other project. And so I'm not exactly sure what faults we can detect, even though it won't tell you, but a fault is a fault. So I'm going to kind of put that in here. Possibly for conditions. There. So just kind of put that there, mainly as a note for me to come back and, to during some of the evaluation phase, because there's a lot, like, again, I keep saying this, there's a lot of work we have to do. There's a lot. And figuring some of this stuff out is part of the work. And we can update the tests to validate, to do everything proper. So I'm not going to worry about that this very minute. Sometimes tests come to you while you're doing other tests. So we might come up with other things we want to test. But right now we want to make sure that we can, for current measured, the driver IC should be able to deliver 2.5 amps of current to a motor. So, and that would be in that test log, PR001. Okay. So, again, this could be a potentially destructive test. You're not really, the system doesn't really expect to constantly drive one of these motors at 2.5 amps Typically, they don't need that much, but as they get loaded down or a mechanical problem happens, like something jams a mechanism up, the motors will try to draw out more current, or the heavier duty motors will. So it's just stuff to consider long term. That's why we're putting in the cooling system. That's why it's pulling all that heat into the PCB, and we're putting the fan on it with the heat sink to account for real world use, to where it could be driving like a heftier motor, a larger stepper motor, where it may actually draw like 2 amps or 2.3 amps. That heat's that's going to heat up the IC. It's got to go somewhere and be dealt with. Otherwise, the chip's going to go into shutdown and trigger the fault condition. But we're going to test for all that. We are going to test for all that. We might kind of, figure out other stress tests for all that. But for now, we'll leave this alone and figure out, work forward from here, iterate forward. I just want to, kind of get more of these thoughts organized, at least into a more cohesive plan. So, -002. All right. Once this test completed, output and disconnect the let's fix this, get rid of that. Wrong. Go up to here. Nope. There we go. Fix that. All right, yeah. So I'm gonna have to kind of maybe even diagram up, a schematic, might even diagram that up real quick. Might even throw it in, in a CAD and have it part of it, once I figure out all the details for the resistors I need. Maybe have a separate BOM for it and everything. We'll figure it out. I'm not terribly worried, but we'll get there. We'll get there. PR002 from CN7, so we have to disconnect that. We can leave the FTDI cable connected at this point. The multimeter we might need for temperature mode. Okay, so enable the and flash the ESP32 with the. So this is going to be basically PCB temperature rise. So let's kind of give it a new folder. PCB temp rise. Fancy sounding names, but with the firmware connect. So we want to kind of get the so we might have to devise a little bit more of a complicated test for this, because basically what we want to do, we want to have connect is basically like the board and standard operation, like it's just day-to-day operating, and we want to leave it set and basically operate a separate motor. Maybe have it do one of those little test fixtures I talked about. Have it actually do something. So actually have it loaded down trying to operate with something. So I might have to actually end up building something. So again, more stuff to do, a lot of stuff to do. So I might actually just try to make videos of us doing things like that. It's going to get interesting. Let's just say that it's going to get interesting, because part of this process in this series is I just want to show what it takes to basically, to be serious and do the work that needs to be done before releasing a product to the market. especially one that you expect to work and all that. Thank you, Blue Squiggles. You helped me find my own spelling mistakes. Connect the stepper motor test rig. So I'm okay. So here I'm going to call it. Just do this. Stepper motor test rig to CN7. It's going to be another pre-wired. So again, if I have to order a few more of those pluggables to have a few free and then to build and make all these different test fixtures, I will. That's not a problem. That's just a couple. That's just a handful of the 4. And I think about 50 of the things. If I'm not mistaken, if I remember what I did, I ordered 50 of those 4 circuit ones. So I should have plenty to make a bunch of test rigs. Warp a bunch of stepper motors and stuff. So I'm not terribly worried. Connect the stepper motor test rig to CN7. So what I'm thinking we should do then is also, I didn't start KiCad. So I want to do this. I'm going to pull up the PCB and kind of show you what I'm thinking of. So I'm not terribly worried about this because we're kind of like looking at PCB temperature rise overall. So what I might try to do is figure out how to, I might see about printing out or, capturing an image of this. And, because I'd like to find a way and modify it and identify, like points to maybe attach thermocouples to. Because I'd like to at least have a thermocouple kind of like attached here, kind of close to the middle of the board. Because all your heat's going to kind of congregate, because, if you got these, we might actually be, well, if we have the test rig, we'll be tied to here because we're going to be monitoring everything here. So, yeah, so we can use this as a bunch of different things. Like we can use the limit switches, we could do that. Control, so we're going to have to tie in all the other stuff. So let's see here to CN3, CN7, to CN7 and CN3 as indicated by the pluggables. Labels. So I'm going to have to dig up all my extruded aluminum, see what parts and materials I have, see what I have to kind of like find, scrounge up, or buy. I have plenty of stepper motors from when I tore down my old 3D printer. I should have enough extruded aluminum to build something to do this test rig. Again, it's just going to be basically I'm going to be testing one of those. We might as well test one of the belts, and we're just going to kind of monitor the temperature rise, at least for let it run for an hour. I don't know how we're going to pull this off. Maybe I'll start running it. We'll figure it out. Maybe we'll make a special stream. I don't know. Again, there's a lot to figure out with doing this kind of stuff and making these videos in the stream. And I don't want to cut too much short because again, it's a process and I feel it's all important, but we'll figure that out. Connect the stepper motor test rig. So I have to do that. Nails on the test rig. We'll leave this alone here. I think that, oh yeah, so the power supplies also get loaded. So we will have to do some loading for these guys. I have to make loading rigs for the 3.3 and the 5 volt because they're going to take separate resistors. Because according to the data sheet for the power supplies, I think the ripple measurement that they offer is loaded at the 2 amp output. And they'll also kind of verify that they can deliver the 2 amps. So we'll kind of like two birds with one stone kind of. And maybe I'll put those in as performance requirements as well. Deliver the 2 amps. And we'll account for that. So again, a lot to do, a lot to cover up. A lot to cover and then get going. So what I'm hoping is my PCBs come in tomorrow. We can at least check them in. I don't plan on building anything tomorrow, but they should be here. We can check them in, test the new webcam setup. It won't be perfect, but you know what? It'll be better than it was because I've got a ring light for it. So it should give at least better images. I got to organize, got to do some cleaning because my workspace is atrocious right now. And in order to show any of this stuff, I don't want to have to be tripping over my own crap. So I'm just going to say that I got a lot of stuff to organize and put away. So I'm going to work on that today. Tomorrow, I still have a PLC program to write. So a whole bunch of other stuff to do. So even if we do get the boards in, we may try building like Wednesday. So we'll check in the boards and the stencils if they come in tomorrow. We'll check those in, kind of get that process done. Maybe work on some more documentation. Maybe build on Wednesday. At least build the pilot board. That might actually take the full stream time because to hand populate and reflow double-sided board can take a couple of minutes, can take a little bit of time because you got to wait for things to cool down. And then to hand solder the other side or all the through holes will take a little bit of time. And I might have to kind of like flip the camera around and stuff, move it around to my other workstation. I've got a lot I need to solve, a lot of little details, a lot of little moving parts. Because again, this is all new to me and I'm advancing and buying stuff as I go to make it all work. So just bear with me and be patient. I'm going as fast and efficiently as I can with what I have to work with. So for now, I'm going to call it here. The video's already over an hour. And hopefully tomorrow we get boards in and we can all have fun opening them and checking them out. Yeah, you're welcome for the streams. It's been an interesting process and something different for me. Format I wanted to try because not everybody uses YouTube and some people do like seeing it first before the editing happens, before it gets posted. So I've been having fun. I might do more streams on the other subjects. I don't know yet, but so far my plans are straight to YouTube videos. But who knows, that might change. That might change depending on feedback. So I want to thank you for checking us out, for sticking with us this long, and see you tomorrow around 6. Have a good rest of your Sunday, and take care.